Hi! Today we will not talk about physics and just do a mathematical detour for pure enjoyment. In the previous video, Imaginary Numbers Reimagined, we defined a multi-dimensional number set from first principles. The complex numbers are a subset of this. Let's start with the most basic question. What is a number? Not the representation of numbers, those are just symbols. What is the essence? Numbers are abstract objects defined solely by the relationship to other numbers. We visualize these as nodes in the network, connected by functions that transform one number into another. The existence of an infinity of such number objects is axiomatic. We take it as given. We pick one at random and call it 0. This is a definition. This is slightly different to how we did it in the original video, where I made the existence of 0 an axiom. An axiom is a hopefully evident assumption that is taken to be valid as the starting point for logical reasoning. We will define 6 axioms and then construct, piano-like, a number system. What makes one number different from another? We need to relate them to each other. We use unary functions for this, shown here as these grey arrows. A unary function is a function with only a single argument. It takes a number object and transforms it into a new one. Traditionally, mathematicians use functions that have a defined domain and range. We call our functions open functions because they have an open domain. Any open function can be applied to any other object, and we can use their range to define new sets. So, for example, here we can also apply the function f to q. This way we can generate a set created by the function f. We denote repeated applications of an open function to an object with a superscript. This is used as a shorthand notation, so instead of saying f of f, we can just say f to the 3. It's a philosophical question which is more fundamental, the numbers or the functions that connect them. You could define a function as the relationship between two numbers, or you could define every number as something generated by the repeated application of a function to a single starting point. Both views are coherent, I think, but I prefer the latter. Out of all the possible functions, we pick some that follow certain rules. We will pick the functions that are commutative. If we apply a sequence of functions in a different order, we will still arrive at the same result. The functions are bijective and all have an inverse function, noted with a superscripted star here. In the diagrams, we'll show the inverse functions as dashed lines of the same color, with the arrow pointing in the opposite direction. Bear the symmetry in mind though, which arrows are solid and which are dashed is entirely a matter of definition. We define two types of these unary open functions, chains and loops. Chains, which we denote as inc, create an unending sequence of new objects. Each application of a chain function takes us to a new, previously unreached number. If we start at 0 and repeatedly apply the inc function, we generate what we typically call the natural numbers, 0, 1, 2, 3, and so on. Loops, which we denote as rot, cycle through a fixed set of numbers. A loop of order n returns to the starting point after exactly n applications. The simplest loop is order 1, the identity function that maps a number to itself. Order 2 loops give us negation. Applying the function twice returns us to where we started. Order 4 loops give us the Gaussian integers, which are complex numbers with integer parts, where the rotational constant I performs a 90-degree rotation in the plane. What we're doing is to define I as what we call a fourth-order rotational constant, rather than the square root of -1. For higher orders, we often get more dimensions. We skipped over order 3. Order 3 gives us 3D numbers with rotational constant j that we can use for operations in 3-dimensional space. And we can keep going to arbitrary dimensions. Pure order 5 gives us a 5-dimensional space, and so on. To recap, these are our axioms. For a more detailed treatment, please check out video 4. Axiom 1 was about the existence of numbers and to pick one as our fixed point, 0. Axiom 2 says that two objects uniquely define the function between them. Axiom 3 says that there is effectively only one unique loop per order. You may have multiple functions, but they all traverse the same numbers on a loop, just in a different order. An example would be multiplication by positive I and negative I for the order 4 loop. Axiom 4 defines order 2 as a special case. Here we have an inc function starting from 0. The dotted line is the inverse. When we apply the dotted inverse function to 0, then we get another chain. We can associate every nth object on one chain with the nth object of the other chain, and we will use the rod2 function for that. This makes intuitive sense. If you take +1 as the inc chain, then the inverse is -1. So we use times -1 to map between them. Axiom 5 connects the loops and chains together. Now we have integer chains radiating out from 0 in all dimensions. And each nth element of a chain is in relation to the nth element of other chains through rod functions. Now let's use chains and loops to actually build a number system, order by order. When we apply a single loop of order n, how many new dimensions does it contribute? For odd orders, the answer is simply n. For even orders 2n, it's only n because the order 2 subloop is not making any extra dimension because of axiom 4. As we layer orders on top of each other, the combined loop order is the least common multiple of all orders so far. The dimension count follows the same rule. Order 1, the natural numbers. Order 1 is just the one-dimensional inc chain from 0. Order 2, the integers. Adding the order 2 loop reflects the chain through 0 and extends it in both directions. We now have all the integers, so it's still one-dimensional. Order 3, 3 dimensions. Adding a rod 3 loop introduces a new rotational constant j, where j to the 3 is 1. A general order 3 number has 3 integer coordinates, and thus we call it 3-dimensional. Remember that j and j squared are not complex roots of unity, but independent dimensions. Order 4, 6 dimensions, but with structure. Adding a rod 4 loop introduces I, defined here as a 4th order rotational constant, not the square root of -1. On its own, let's call that pure order 4. This gives the Gaussian integers, complex numbers with integer parts, living in a 2-dimensional plane. But order 4 carries everything from orders 1 through 3 as well. The combined loop order is least common multiple of 1, 2, 3, and 4, which is 12. So this is also pure order 12, which is even, giving 6 dimensions. 6 coordinates, but they aren't all equal. There's a hierarchy. We can regroup. This looks like a complex number whose 2 components are each 3-dimensional order 3 numbers. This nested structure is reminiscent of a rank 2 tensor. I think it's nice that something similar to tensors pops out of this number system on its own. Maybe a topic to return to in the future. Let's draw all the 12 nodes of order 4 in a circle. This one here is generated by the repeated multiplication by ij squared. Let's take a look at the subloops. These are the order 4 subloops. Here are the order 3 subloops. And finally the order 2 subloops. Remember this, we'll do something similar later, but not with loops, but with chains. Our number system has addition, subtraction and scaling, but no general multiplication between multidimensional numbers. This is a deliberate choice, and it is worth explaining why. In our construction, all the axes of a multidimensional number are equal. There's no preferred direction. If we take a 3D order 3 number and permute the coordinates, cycling j to j squared to 1, you get a different number, but the underlying structure is identical. The axes are interchangeable. General multiplication between 2 3-dimensional numbers would break this, because one element must play the role of the multiplicative identity, the number 1. Now the 1 axis is special. Multiplying by 1 leaves everything unchanged, but multiplying by j rotates. The axes are no longer interchangeable, and the symmetry we built in from the start is lost. Why do I want interchangeability? I want to be able to express 3D spatial coordinates as order 3 numbers. If you don't care about that, you can still define multiplication using the standard distributive rules alongside our loop relations. The downside is that you don't get a closed set. This is a corollary of the fundamental theorem of algebra. The only commutative algebra over the reals that is closed under division is the complex numbers and some of its subsets. Here is an example of a zero divisor. These are 2 numbers, each non-zero. When you multiply them, then you get a 0. For my part, I'm not totally on board with this insistence on closure under division. A visual example. Here is a well-defined two-dimensional function. And here's one where the black areas signify unreachable places. Yes, the one on the left is regular, but the one on the right is interesting. If you plotted the points x, y, z, where this results in a 0, what would that shape look like? Now we should also mention a couple of other ways to preserve multiplication. The first one is cyclotomic fields. All the laws of our rotational constants have already been explored. Sadly, cyclotomic fields have already bagged the lovely term roots of unity, which is nicer than rotational constant. They behave similarly, with the difference that the roots of unity are not new dimensions but complex numbers. Here is a 12-element loop in the complex plane. This looks like pure order 12 earlier, but here each node is a complex number, so the 6-dimensional structure is squashed flat, while preserving multiplication. Another way to define multiplication that preserves division is to lose some laws. First of all, commutativity. The set that does this are the quaternions. These are 4-dimensional. Traditionally, the dimensional constants are called 1, I, j, k, but please note that j is not our order 3 constant. 1 is our normal identity, but I, j, k are all loop 4 constants, so they violate our axiom 3. Quaternions are not part of our number set. They also break commutativity. There are more exotic sets beyond this, for example the octonions. The general term is hypercomplex numbers, but they are all outside the sets we defined here. So far, everything we've built is equivalent to integers, albeit in multiple dimensions. Let's extend the framework to include fractions. Consider any two consecutive integers on a chain, say 0 and 1, connected by inc, which we can think of as plus 1. What if we want a number setting between them? We introduce intermediate number objects and a new chain functions to reach them. The simplest case introduces single new chain functions d2, where 2 steps equals 1 inc step. This gives something equivalent to a step size of a half. Between 0 and 1, there's now one intermediate point. We can call this set pure Q2, all multiples of a half generated by D2 alone. Pure Q3 comes from D3 alone, step size a third, 2 intermediate points between 0 and 1. Pure Q4, step size a quarter, 3 intermediate points, although note that a half is already familiar. This is directly analogous to a pure order loop, a single rod function of order n considered on its own. We don't want the previous points to get lost, so we stack the new chain step sizes on top of each other. Start with nested Q2, just the integers and the halves. Add Q3, keeping Q2. The finest step size is now a 1 over least common multiple of 2 and 3, which is a sixth. 2 new points appear between 0 and 1, a third and 2/3. The point 1/2 was already there. Add Q4, keeping everything else. Least common multiple of 2, 3, 4 is 12. 2 more new points, a quarter and 3/4. The point 1/2 was already there. Just as in the loop case, applying D4 twice gives D2. This looks familiar. Remember the 12-element loop we showed before? This is the chain equivalent. You get the same structure. Prime order steps generate new points, common divisor orders share points. As we nest more and more orders on top of each other, we can make any fraction. At the limit every fraction is reachable, we have generated the set Q. I would like to introduce the concept of isomorphism at this stage. When you have two separate structures that are identical, you may as well consider them to be the same thing, until you relate one to another. Here is an example. This is the chain made by the functions +1 and +2. And this is the chain made by +1 and +1/2. You notice they look identical until you relate them to each other. We will return to the concept of isomorphism later when we talk about infinity. Every integer is finite. You can always reach any particular integer from 0 by a finite number of steps along the chain. but the set of all integers is infinite. Infinite is a property of the set, not any individual number in it. Recall axiom 1. Infinitely many number objects exist, and we picked one to call 0. We will write our final axiom 6 similarly. We choose omega for two reasons. It is the last letter of the Greek alphabet, and it bears a visual resemblance to the familiar infinity symbol. They are not the same. In standard mathematics, infinity behaves more like a concept than a number. It appears in limits, in statements about unbounded sets, in the extended real line, but arithmetic with it is either undefined or collapses. Omega is different. It is a specific number on the chain, and all the usual rules of arithmetic apply to it without modification. Infinite is simply a property omega has, like being even or odd, not a special status that suspends the normal rules of arithmetic. Omega plus 5 is the number 5 steps beyond omega. Exactly as 1000 plus 5 is 1005, nothing exotic is happening. Omega minus 1 is one step before omega, still infinite but strictly smaller. 2 omega is twice as far from 0, a larger infinite number. Let's give the integer step chain a name in our hierarchy, R0. We will use Rn to denote chains of progressively finer accuracy. R0 has step 1, R1 will have step 1 over omega, R2 will have step 1 over omega squared, and so on. Now we define a new d-step chain function, not one that creates finite fractions, but one that takes omega steps to move 1 plus 1 step. The step size here is 1 over omega, which we can call epsilon. Let's call that set R1. It is not quite continuous, but we can express any number to an infinite accuracy, meaning omega accuracy. Now we return to the isomorphism. See that these two chains look the same. From 0 to 1 with plus epsilon is equivalent to from 0 to omega with plus 1. And that in turn is equivalent to from 0 to omega squared with plus omega. R1 behaves like the real numbers for most practical purposes. Any quantity expressible to arbitrary but finite precision lives in R1. But strictly speaking, R1 is not continuous. Here is an example. Here the ... means exactly omega 9s. The sum is this. This falls short of 1 by the infinitesimal amount of 1 over 10 to the omega. So in our system, 0.999 ... is not exactly equal to 1. Standard mathematics disagrees. It interprets ... as a limit taken beyond any fixed stopping point. We need to introduce a new symbol for that. What if we apply the chain function forever, beyond all infinities? Let's call this capital omega. Not a number on the chain, but the concept of the entire unbounded process itself. This means that we cannot do addition with capital omega. If capital omega is the absolute biggest, then capital omega 1 would be bigger, so no addition is possible. However, an argument can be made for assigning meaning to division by 0 using capital omega. This also recovers the accepted identity. If we interpret ... to mean capital omega times, then this is indeed 1. We only looked at numbers in the 1 dimension, but both small and capital omega can be rotated into other dimensions. Hilbert's hotel is a famous thought experiment in mathematics. It has infinitely many rooms, all of them occupied as shown by the red lights, yet it can always accommodate more guests. Here's the standard telling. A new guest arrives. No problem. Move the guest in room 1 to room 2, room 2 to room 3, and so on. Everybody shifts up by 1. Room 1 is now free. Now an infinite omnibus arrives with infinitely many new guests. Still no problem. Move every existing guest from room n to room 2n. All the odd-numbered rooms are now free. This is usually presented as a striking illustration of how infinity defies ordinary intuition. But let's look at it again using omega as the number of rooms. So if you want to accommodate an extra person, you would require omega plus 1 rooms. For another infinity of guests, you need 2 omega rooms altogether. The paradox dissolves. But what if you mean a hotel with capital omega rooms? Well, then you can't add any guests because addition is not allowed. As we said, we can't have capital omega plus 1. Paradox still dissolved. The standard presentation uses infinity instead of omega, and in that treatment infinity plus 1 equals infinity. An infinite hotel gains 1 guests and remains equally infinite, so of course they fit. But this is confusing a property with a number. This is like saying this 2-seater sports car has an even number of seats, thus it can accommodate 4 passengers because 4 is an even number. To be fair, I think that Hilbert's point was not about fitting guests in rooms, but to illustrate that an infinite set can be bijectively mapped onto a proper subset of itself, which I'm uncomfortable about. The argument that there are different sizes of infinities has been made by Cantor, and most famously with his diagonalization argument. Let's see what that looks like when we use omega instead of infinity. We write out all combinations of omega bit binary numbers in a table, which then has 2 to the power omega rows. These are every possible combination of omega zeros and ones. Now construct a new number by walking down the diagonal. Take the bit at row n, column n, and flip it. This diagonal number has omega bits. Does it appear in the table? Differs from row 1 in position 1, it differs from row 2 in position 2, and so on. It is not equal to any of the first omega rows. But the table has 2 to the power omega rows, a lot more than omega. The first number that genuinely does not appear is at resolution omega plus 1, a string 1 bit longer than any row in the table. Of course it is not in the table, it's a different longer object. So we have not uncovered a paradox, we've confirmed that omega plus 1 is bigger than omega. In the standard presentation, infinite means the infinity symbol going all the way without end, similar to our capital omega. The paradox comes from using it inconsistently. I'm in no way disagreeing with Cantor's conclusion. There are different sizes of infinity, and the integers and real numbers are different sizes. But this is not a categorical distinction between countable and uncountable sets. In our framework, this becomes the numerical statement 2 to the omega is bigger than omega. Let's talk some more about countability. A set is countable if its elements can be matched 1 to 1 with the natural numbers, if you can list them in any ordered sequence without missing any. A set is uncountable if no such mapping exists. The integers are countable even though they extend in both directions. The rationals are countable by walking through them diagonally. The real numbers are uncountable as per diagonalization argument. In our number system here we don't disagree with the conclusion, but we're not really fussed about countability because this is built into the construction by chains. Instead, we're more interested in the relative size of the various sets. All numbers on the chain are countable as there are a finite or infinite number of ink steps along from the origin. Real numbers have a big omega accuracy. For example, you could approximate pi by 10 digits or by 1000 digits, but also by omega digits or omega squared digits. However many digits you use, there will always be more. In our construction earlier, we used n in Rn to denote the accuracy of each set. The real numbers could be thought of as akin to R capital omega, bearing in mind that capital omega is not an arithmetic number. One of the things I like is that this framework allows us to numerically explore divergent series. For example, what is the sum of all the natural numbers? This has generated quite some controversy online with multiple YouTube videos presenting Ramanujan's argument that this equals negative 1/12. This seems crazy, but there is a connection. How did he arrive at this result? There are a whole bunch of sketchy steps that involve a fair amount of Hilbert hoteling. So what is the real sum? This is quite straightforward if we let ... mean small omega. The sum of the first m integers is given by a standard formula, coincidentally derived in the previous video on this channel. So for m equals omega, it survives the Hilbert hoteling transformations described in the number file video on the subject. I'll just flash them up on the screen if you're interested. It is customary to start with a historical perspective and build on other people's work. But here I was trying to start from scratch and build a number system from first principles. Especially in maths, it's hard to discover something new, so many of the concepts presented already exist, and I'd like to acknowledge them here. There are a lot of generalizations of complex numbers, it turns out. Several I've only found out from video 4 comments. I didn't know about surreal numbers, for example, but it feels good to explore what looks like new land and then spot a John Conway was here sign. They contain all the numbers discussed in this video, including omega, epsilon, omega squared with the same notation. But the construction is quite different. While we started with loops and chains in order to get multiple dimensions, surreal numbers were invented from a game theory starting point. In fact, Conway was studying the game Go. Then there are the hypercomplex numbers. We mentioned quaternions, octonions, etc. already, but there are also split complex numbers. They relate to hyperbolic geometry the same way complex numbers relate to circular geometry. They have zero divisors. And they're not part of rotational numbers because they violate axiom 3. Dual numbers. These are numbers of this form. Here epsilon is not infinitesimal, but a value that when applied twice becomes 0, a nilpotent element. As far as I understand, they're also not part of rotational numbers. Cyclotomic fields. We covered those earlier. Silvio Olariu's book Complex Numbers in N Dimensions is the closest work to our construction of rotational numbers that I could find. It systematically explores generalizations of complex numbers in higher dimensions. Olariu's three-dimensional case is exactly equivalent to our order 3 rotational numbers. For 4 dimensions he finds several distinct systems, of which our order 4 system is one. The key difference is axiom 3. Olariu allows multiple distinct algebraic structures per dimension, resulting in a richer catalogue of algebras, while we limit ourselves to only one loop per order. Transfinite numbers were proposed by Georg Cantor, although he was not particularly appreciated in his time. Cantor developed 2 related systems for studying infinity: ordinal numbers, which measure order in position, and cardinal numbers, which measure size. Ordinal numbers produce a hierarchy extending beyond omega into omega squared, omega to the omega, and beyond. Cardinals have their own hierarchy: aleph 0, aleph 1, aleph 2, etc. In ordinal arithmetic, omega plus 1 is defined and strictly greater than omega, exactly as in our system. However, in Cantor's system, ordinal addition is not commutative. For cardinals, aleph 0 is the cardinality of the natural numbers, corresponding to our omega as a measure of set size. We've only concerned ourselves with absolute numbers, not with the cardinality measuring the size of infinite sets. Finally, Cantor used capital omega for the absolute infinite, the totality of all ordinals, which is too large to be a set and sits outside of arithmetic. This is our capital omega, but without the religious overtones implied by Cantor. It turns out we didn't invent this notation either. Differentiation. A natural way to apply our number system could be to make differentiation more flexible, easier to understand, and also more accurate. The usual notation is d over dx of f of x, which flummoxes me frequently. On one hand, it's a shorthand for a limit. On the other hand, sometimes you can treat dx and dy like a fraction, for example in the chain rule. Say we use this function as an example and then calculate the derivative using infinitesimals. Now we explicitly use an infinitesimal instead of a limit. For our function we get this. We'll just sweep the last 3 terms under the carpet because they're infinitely small. Or, if you want more accuracy, you keep them, but then bear in mind that you're actually calculating the gradient of the function midway between x and x plus epsilon. We can use a better formula that calculates the gradient more accurately at x. When we work this out, we get this. As it turns out, this approach also exists already since the days of Leibniz and has been made rigorous in the 60s under the name of non-standard analysis. So I maintain this is a nice way to derive a multidimensional and infinite number system, but what is it useful for? Well, for a start, I find this derivation more natural and not prone to paradoxes. The main use we have in this channel is for fundamental physics. The order 3 numbers have 2 uses. For one thing, they offer a way to express spatial 3D coordinates, like you can use complex numbers to express 2D. Furthermore, they're useful to describe the nuclear strong force. Electromagnetism is closely related to order 4 numbers, but the theory that describes the strong force, QCD, uses color names. This is weird because every other property of particles is a number. Order 3 numbers supply the threefold symmetry that is missing, and I feel that negative J makes more sense than anti-green. Higher orders may also be interesting. Hey, maybe tensors turn out to be useful in physics. For pure maths, the most obvious use is to be able to numerically explore divergent series. We could also try to use an epsilon-based derivative method for smooth functions. What about fractal functions, distributions, or cases where the standard limit fails? We have yet to explore infinite loops. Particularly interesting infinite loops would be the order of omega factorial and the smaller infinite set of least common multiple of all positive integers. Both of those contain every finite loop as a subloop. We have axiomatically derived a number system from loop and chain functions. This includes integers, multiple nested dimensions, multiple nested infinities. If I made mistakes or reinvented the wheel, please let me know. I'm interested in how much you agree and disagree with my take, and look forward to a spirited discussion in the comments. Thanks for watching.